Hello everyone, we are Team Zebra and our project is a continuation from last year's project, Printer Real-Time Torque Measurement. Our technical director is Matthew Corviz, a URI Mechanical Engineering alumni who graduated with a bachelor's in 2008 and got his master's in 2016. This year we have a team of three. We got me, Kevin Suggs, we got Dean Graposo, and Roy Oza. I'm the team's computer engineer and will be a part of the class of 2023. Dean and Roy are the team's electrical engineers, but Dean will be in the same class as me, 2023, and Roy will be a part of the class of 2022. Alright, so let's talk about Zebra. Zebra Technologies is located in Lincoln, Rhode Island, but have many other locations around the world. The company was established in 1969 and is the market leader in mobile printing technology, but is also the industry leader in areas such as barcode scanning and specialty printing. So the motivation behind this project is very similar to last year's, but with some added stuff to it. So first and foremost, we want to continue to improve the fixture design by interfacing the transducer, interfacing all peripherals to one device, and taking that device and putting it on a printed circuit board. In addition, we want to try to implement a GUI, or a graphical user interface, to handle the operations of the device and gather and output data to the user. The best outcome of this is first interfacing the transducer by gathering signal data from it and connecting it to the GUI. Second, having ease of test, which will give us a user-friendly interface and faster troubleshooting. And third, having it be versatile so it can be applied to all or many printers. But did we reach our ABO? Well, no, but we got very close. What prevented us was the STM code, which gave us a nigh impenetrable roadblock that even our TDs had trouble with. But after that roadblock, we would only have to bring 3 sets of code together in order to reach our ABO. However, we made plenty of contributions along the way. For example, the GUI and the filter completely fulfills its functions. The ADC also works as intended. The transducer has been integrated into the fixture, and there's plenty of documentation to help the next team start smoothly. To go a bit more in depth on the contributions, for the GUI, it can do background calculations, serial communications such as send and receiving data, and it has graphing capabilities. For serial communications, we have done that between Python and C programming languages, and we use PuTTY as a form of testing, and we also worked with variable manipulation such as data type conversions. When looking at the fixture, we have done work at interfacing the dev bench by fixing the last year's code and checking the functionality of the driver board. In addition, we created entirely new separate code for the ADC to set up a system for grabbing voltage data from the transducer block, and this data is completely loggable and graphable. For the hardware, the team has assembled a low-pass filter that has a cutoff between 100 and 1000 kHz. This was done by first assembling all the components on the breadboard, and then, once it was verified, build it on a PCB, which you can see with the picture right there. This filter is supposed to interface with the transducer, but before that, we had to gather signal data to be sent to the GUI, and we had to solder and label all the connections. The success of this project will have an economic impact on the company because it will give it much more reliable data collection, and because of that, it will reduce costs by lowering budgeting towards troubleshooting and reduce risk of malfunction. Now this is our simple block diagram, but there's something missing. Ah, yes, the GUI. The GUI should be connected to the microcontroller as it will send and receive serial data from it, but the GUI wasn't the full extent of my responsibilities. I also had the responsibility of being the team's manager, making sure we all had good correspondence with our TDs, whether that be through communicating through Microsoft Teams, setting up meetings or additional meetings, and making sure that everyone can attend, or at the very least be a liaison for both parties when one of us was not available. I was also responsible for all emails, forms, gathering all the hours from the logbook, and submissions for the entirety of the project, as well as making sure that we had good documentation on all of our code files, our shared OneDrive, the Taiga Kanban that we used back in the fall, and the best track that we used this spring. So basically, I handled all the paperwork for the team so that my team members can focus more of their time and energy on the project. Let's not forget about the GUI. The GUI was an aspect of the project that only I worked on, which makes sense because I'm the CP of the team. We needed the GUI to run using Python, and since I never used Python or made a GUI before, I had to do quite a bit of research before embarking on this journey. And through that research, I was able to find out that the most easiest and straightforward way is to use Python's built-in tkinter environment to construct the GUI. And thanks to Python, implementing serial communications was relatively easy, but it was a bit of a challenge when getting the label to appear correctly on the graph. At first, the label was all over the place, and the plot and the label's aspect ratio was out of whack. But after meeting with my TD and doing some research together, we were able to find out that there was a function that we can set the aspect ratio so that it comes out perfect every time. But outside of this, the biggest challenge was interfacing the GUI with the microcontroller, as that posed many roadblocks. Those roadblocks completely halted the development of the GUI, as our main focus was ensuring that the microcontroller had consistent data transfer over serial communications. And some of the ways that we would dealt with this was by working with data type conversions and multiplexing. And in the end, the GUI is more or less fully operational, but is still on tkinter, so it doesn't look the best. So you're all probably tired of listening to me now, so now I want to pass it off to the next designer, Roy Oza.
Thank you, Kevin. So right here, this diagram shows that this is the fixture motor that moves the printer's plan move at its pace. The printer then sends the signal through the microcontroller with the GPIO, which comes from the low-pass filter I made, and pass the received signal through the stepper motor driver DRV8424, where we output the micro-stepping resolution into the hybrid stepper motor. We would have connected the Python GUI and the STM32 code along with my filter and interfused it with the transducer, but we never got the code to work. As we move on to the next slide, I designed a high-pass filter circuit and a low-pass filter circuit design. As we realized throughout the project, we wanted a low-pass filter because we don't want to capture the fast, instantaneous spikes of torque, and those frequencies were carried over from our existing fixture. That was correlated to our motor tester. The higher frequency torque spikes don't result in stalls because they are so fast we want to filter them out. I researched what it was supposed to do and the sizes and components we used, as we needed to add another capacitor to our original circuit and change the op amp from LM741 to an OPA AID 374, as we had to follow the pinout for the low-pass filter circuit design to work. To make sure it worked before, I tested it on multisim first, and then through lots of trial by error on the oscilloscope, we got a clear signal from 0 to 100 Hz, and then the signal to cut off from 100 to 1000 Hz, which is the definition of a low-pass filter. In this process, I calculated gain and frequency and wanted the cutoff signal to be at 100 Hz. I then organized a pinout for the Nucleo board in DRV8424. We solved the issue from last year's team and rewrote a new pinout legend. All out of order so we could use a transducer. As we go on to the next slide, I researched ideas on how we were going to interfuse it with the transducer. I looked at how we were going to use the low-pass filter with the transducer, and I also researched how signals of the transducer will help print labels, and getting the right torque measurements and data from labels. We never got the STM32 code and the Python GUI code to work, so we never got to test it out. After my low-pass filter was made, I helped out with the code that will help the transducer with the printer. I helped come up with code that will help print labels easier, and I also helped connect the software to the hardware. I assisted with Kevin and Dean and tried to fix the errors and troubleshoot and come up with new ideas to get the code to work. Now I will pass it off to Dean.
Thanks, Roy. So for my portion of the project, I was primarily working with the physical setup, which included the stepper motor driver, the transducer, the printer itself, and of course the Nucleo board that we were using to code and run the whole setup. So I was tasked with fixing errors from the previous team's code and interfacing the transducer so that we could get data out and send it to the GUI. For the first semester, I was primarily focused on fixing the errors, changing the circuitry, making sure that everything was robust and tight and could work. And for the second semester, it was focusing more on the transducer and the analog to digital conversion that we would use to get graph data. Concerning the STM32 Cube IDE, which is what we use to create code for the Nucleo board, I ended up finding a couple of the errors from the previous team that were causing the setup to hold back on high Z inputs, which is what the servo motor uses to go through the different microstep modes of the printer. And I managed to start working through the analog to digital conversion, and I made a very primitive set of code so that I could get values out and create graphs from the transducer. The transducer itself, I made physical connections to the transducer using wired circuitry, and I ended up processing signals and verifying their correctness using an oscilloscope and a function generator. And because we had a set voltage limit on how we could actually get the system to send voltage data out, I had to create a voltage limit by using a voltage divider. For the second half of my contributions, I improved the signal processing that I had set up initially. I managed to improve the resolution on the signal out by increasing the sample rate, and I also adjusted the internal clock by making an entirely separate set of code in order to create a faster sampling rate so that the signal could actually look better coming out, which was very important. So that way we could actually get those tiny little changes in the transducer as it was running. I finished off by redesigning the circuitry. I improved the circuit setup, and I made sure that there was some robust documentation so that the next group who ends up working on this can find the correct pinouts. And I combined all of the boards together so that they could stay together and rearrange the fixture so that the wires in their current setup wouldn't fall out, which was an issue that we were having for quite some time.
To conclude, we would like to mention our key acknowledgements. We would like to give thanks to Matthew Corvais for proposing this project for our team to work on. And of course, we would also like to thank Dr. Hari Sunak for organizing this program and giving students like us the opportunity to work together on real-world problems such as these. We would like to extend special thanks to Patrick Hagarty for his technical support and help with the STM, and Anna Skelly for answering any questions we had and giving us tips while working in the lab on this project. And with that said, we conclude our presentation on our torque measurement project for Zebra Technologies. Thank you very much.